All right. It's going to be great. Okay, so let's continue talking about sequences then. That's what we started talking about last time, and I want to get down to some more serious matters regarding sequences. All right. So a sequence, remember, is just a list of numbers, one after another. So they could be something like 1, a half, a third. This is a fairly simple sequence, etc. Usually you write a few of them and then put the dots, and hopefully the pattern is clear. This is a sequence. It's more useful if you really want to do something fancy with the sequence. It's more useful to write a formula. So this sequence would also be written, and our book usually writes it like this: AN equals, and then some formula with n's in it. Can anybody say how do you make those guys with a formula? This is a fairly straightforward one.
1 over n.
Yeah, 1 over n, right, because this looks like 1 over 1, and then 1 over 2, and then 1 over 3, and then 1 over 4. Yeah, so I'm going to say this is like 1 over n. Now, if you want to be very specific about the fact that I'm starting the n's with 1, the way that they write that in our book, although usually we're not going to write this because usually it's going to be clear, but if you want to be super specific about it, you would write in that way. This means I start the n's at 1, so the first term is 1 over 1, then 1 over 2, and so on, up to infinity. Basically, every sequence always goes up to infinity. The only thing that you should be wondering maybe sometimes is where do I start the n's. But all right, great. Or how about something like 1 half, 2/3, 3/4. How you like this? 4/5, etc. Can anyone give me a formula for that one? AN equals, what do you say?
N minus 1 over n?
N minus 1 over n. Yeah, great. It's still just the same denominators as the one up there, but the numerator now each time is 1 less than the denominator. So this is n minus 1 over n. Excellent. I would like to talk, how about one more, just for fun. How about, this is a little something that we talked about last time briefly. This is the same as that other one, but I am alternating the signs every time. Anybody recall, how do I make that happen? So the formula here is basically that again, but I want to add something in there that makes the signs alternate back and forth. 1s and minus 1s, plus 1s and minus 1s. We had an example last time that worked like that. Yeah?
You start with negative 1 to the n.
Yeah, let's just multiply that thing by minus 1 to the n. And the effect of that, so the n minus 1 over n, the fraction part just makes those same fractions again, but the effect of this out front is every time the n's are odd, this ends up being a negative 1, and every time the n's are even, this ends up being a plus 1, and so that causes the signs here to alternate, minus, plus, right? Great. This is a cute little trick that comes up fairly often. When you see minus 1 to the power n, that is an alternation of signs. Yeah.
How does that work with, because 1 is the first term in this sequence, and 1 minus 1 over 1 would be 0?
Oh yeah, you're right. I'm sorry. This is all. I should have started each of these with 0. Not the very first one, but this one here and this one. They should begin with 0, because this is what you meant, right?
Yeah.
Yeah, because when you start the first term, yeah, thank you for that. When you begin with n equals 1 here, the numerator is 0 over 1, which is 0, right? Yes. After my blunder last time, I decided I'm going to make sure not to make any stupid mistakes today, but I already failed in my goal. Sorry about that. All right, and this one also is 0. You could say it's minus 0, but it's 0, right? Excellent. All right, thanks for that. Let's talk about what I would like to talk about, at least for the next few moments, is sometimes a sequence sometimes sequences have a limit. And this is a big thing that people care about with sequences, is what is the limit of this sequence. And I hope that on some basic intuitive level, everybody kind of knows what I mean by that. Like, for example, this very first one that I wrote, 1, a half, a third, a fourth, a fifth, etc. This sequence actually does have a limit. This, of course, is an equals 1 over n, right? This sequence does have a limit. That is there a specific real number that these numbers kind of approach as you go down the list? They get closer and closer to something or other? Can you say what? Are they getting closer to something? They are, actually. I saw somebody giving me the hand signal. 0 is what they're getting close to. Yeah. These fractions, they always have 1 as the numerator, but their denominators are getting increasingly large. If you like, you could write these as decimals, and you will see that these do get closer and closer to 0. So here, we would write that as lim an equals 0. Now, our book actually writes, oh no, the Red Cross, sorry. They are on me. Like, I donated blood a few weeks ago, and it's like they're calling me every day now. Hardly makes me reconsider helping my fellow man. They have a pretty cool app, though. You can, I have to donate blood often because of my genetic blood condition that you all know about. But if you use the Red Cross app to do this, it actually, you can see a map of where my blood has gone, like where the people who received my blood eventually, where it goes. So that's kind of cute. But they call me all the time, though. All right. Anyway, this is the limit of the sequence. That particular sequence goes to 0, and this is written in that way. Lim n goes to infinity, an equals 0. Or if you're not talking about an, oftentimes they will just write something like this. Lim n goes to infinity, 1 over n equals 0, right? Very natural way of writing things. What about that other sequence? This one, which was starting with 0, of course. 1/2, 2/3, 3/4, etc. N minus 1 over n. Can anybody say, what does that approach? I mean, maybe it doesn't approach anything, but this one actually does. Yeah, yeah, this approaches 1. All of these fractions, they are actually, every one individually is slightly less than 1. But if, again, you could plug these into your calculator if you really want to, but in the long run, generally, in the long run, the numerator and the denominator basically are going to be very close together, which means the fractions values will approach 1. All right, like so. How about just that other one example where I was alternating the signs? I believe the 1/2 had a plus sign. And the numerators were always 1 less. 3/4 minus 4/5. Right? This one is minus 1 to the n minus 1 over n. Any ideas about this one? Does it have a limit? And if so, what does it approach? As usual, you could try to plug these values into your calculator if you wanted to see if they approach anything. Anybody have a feeling about it? Yeah?
Does not exist.
Does not exist. Why do you say I agree?
Oscillating positive and negative.
Yeah, these things are oscillating positive and negative. I would say actually if you focus on the even ones, they are all positive, and those ones are approaching positive 1. For the same reason that this thing approached positive 1. But the odd ones are all negative, and those ones are approaching negative 1. So some of them are approaching one value, some of them are approaching another value. Overall, that means there is no single value that everything approaches. All right, so this limit here, I'm going to say, I'll write that in. This does not exist. All right, because these values, some of them are approaching 1, but some of them are approaching negative 1. And n. So altogether, the whole sequence does not approach any particular value. All right? I would like to talk briefly in some depth about what it means when we talk about a limit. So, what exactly does lim n goes to infinity mean? This is one of those things that there is a certain time in every young math student's life when they think for the first time closely about what it means when you say the limit equals something or other. And I don't know if you all have experienced this singular moment in your life before this point. As in my experience, typically high school teachers don't really talk about this with a lot of detail, and it's because actually it's very complicated if you want to talk about this in full detail. But what exactly does this limit mean? Like, specifically speaking, if lim n goes to infinity of a n equals L, what does that mean? This means... Anybody want to give an attempt to say what that means? You could imagine explaining to your younger brother or something. When I say, for example, lim n goes to infinity, 1 over n equals 0. What do you mean by that when you say that, or when someone says that to you? This is not meant to be a trick question. Maybe I shouldn't have said all that stuff about this is actually very complicated.
When you plug in like higher and higher values of n into your like function a,
Mm-hmm.
the number you're gonna like get closer and closer to is L, but you're actually gonna hit L.
Yeah, great. So I'm going to try and write down something like what she said. In the case of, she was talking about ANs and Ls. Maybe let's just focus on, let's talk about ANs and Ls. So this right here means something like when n gets higher and higher, is this an accurate depiction of what you said? I think so. When n gets higher and higher, then the values of an get closer and closer to L. I think that's more or less what she said. When n gets higher and higher, the values of an get closer and closer to L. This is what most kids or high school students or whatever, most young people are told that this is what the limit means. And this is a perfectly fine sort of operational idea. It gives you an idea of what the limit means. But I would say when I look at this with mathematicians' eyes, when I see something like this, higher and higher, I'm a little unsure about precisely what that means. Like, I wouldn't really say that this, what I wrote in quotes, I don't think that really qualifies as a real mathematical definition, because higher and higher, and also I don't like closer and closer. Like, if I'm talking very specifically using technical terminology and you say closer and closer, I would say, well, how close do you mean? Anyone have a response to that? When you're talking about a limit, it gets closer to whatever. What do you mean closer? Like, how closer? The answer is really, really, really close. That's what sometimes people say. Like, really close, really, really close. Sometimes they say it 3 times. And similarly with this higher and higher, like, how big does the n, you imagine the n is really big, and then this gets close to 0. Well, how really big is the n actually? How big are you imagining the n to be? Like 10? Is that big? Not really. Maybe like 100? Maybe like a million zillion? It's hard to say precisely what is meant by these words. All right. So this, in a more, I kind of view this sort of language is very similar to kind of saying things like, you know, son, when a mommy and a daddy love each other very much, that's where a baby comes from. Like, that's kind of similar language, which is meant to give you say this to young math students to give them some idea of what you're talking about, but actually this is not satisfactory as a real mathematical definition of anything real, right? This is just some kind of language to give you some idea of what everybody's talking about. And this language is actually, I don't mean to be down on high school teachers or high school students or whatever, like this language actually can get you very far, because I was asking you questions about what are these limits, and basically everybody knows what I'm talking about when I say limit, even though what I'm trying to convince you of right now is this is not a good definition. So we need a real definition of what a limit is. You can actually get pretty far in life without using the real definition, as you know. Like you already know lots of tricks for finding limits of various things, even though all of those tricks are based on this sort of superficial understanding of what exactly we're talking about when we say limits. Now, I will say this is, in my opinion, quite complicated, and it's actually not something that we're going to get a lot into. We're not going to do this very seriously in this class, but if you're a math major, you will eventually take a class called Real Analysis, which is all about sort of talking about limits in a mathematically sophisticated way. So that's a little something to look forward to if you're interested. But I will tell us what is the real definition of a limit without using phrases like higher and higher and closer. So here is the sort of modern understanding of what limits really are, where modern means something like in the late 1800s is when this stuff was finally worked out. Interestingly, after the invention of calculus, like even the people who created calculus didn't, from a modern point of view, they didn't have a proper understanding of what actually a limit means. Anyway, what this means, so closer and closer, we have to say exactly what we mean when I say closer and closer. So when I say closer and closer means, to say this in a slightly more technical language, closer than, you could say closer and closer. Do I mean like two numbers being close, like within a half of each other or within 0.1? I mean closer than any number. Any number you can imagine, it's even closer than that, right? If you can think of a really small number, I'm imagining this to be even closer than that. And then similarly, with the higher and higher bit, the sort of actual meaning of that, sorry for all the crazy arrows, this higher and higher means, I'm going to interpret similarly, this means higher than any number. So not just higher than 10 or a million or whatever, it's whatever number you're thinking of is higher than that, all right? That's the idea behind what we now view as sort of the true definition of the limit. So let me try and write the definition as it is understood in modern times. So here is a definition. And the definition is lim n goes to infinity, an equals L means, this is the definition of what the limit means. I'm going to say something about when the n gets higher and higher, the an gets closer and closer to L. And I'm gonna have to write this sort of in this might be a little hard to copy down. Sorry. I'm gonna insert something at the beginning. So leave a little space at the beginning. What I'm going to say, I'm going to write the higher and higher bit first. For any number n, I'll make it a big N. This is about the higher and higher thing. Higher and higher means higher than any number you can imagine. And this big N is meant to represent any big number that you can imagine. So for any number, big N, if the little n is bigger than the big N, So what you read from this part is higher than any number, right? The big N can be anything, and I am imagining that the little n is even bigger than that. If the little n is bigger than the big N, then the sequence is close to the limit. And the way that we write closeness, because you don't know if the sequence is approaching sort of from below or from above, I'm going to write this in terms of absolute value an minus L. The meaning of that is this is the distance from an to L. And that distance, I want to say, is getting smaller and smaller. But instead of saying, I'm not going to say those words, smaller and smaller, I'm going to say this is less than any number you can imagine. And so what I'm going to write is this is less than epsilon. This, I'm not just trying to be fancy here, but when people write this definition, they always use this Greek letter epsilon. And the epsilon actually goes at the beginning. This makes it sort of extra confusing. It will say for any epsilon, which this epsilon has to be greater than 0. And this is a typo. I shouldn't have said for any number n. I should have said this is a technical distinction, which is technically important, although the idea is the same either way. So the full interpretation of all of this, I'm going to try to scribble in here. This means the distance from an to L is smaller than any number. All right? All of this is the true definition of what it means when you say the limit n goes to infinity of an equals L. This, in my opinion, is very confusing, and if you show this to a kid, they will immediately not know what you're talking about at all, because it's just a bunch of weird inequalities. Like they don't even like telling the difference between what's greater than and less than. But so you have to imagine, if you're trying to teach ideas from calculus to kids, you can either say this or you can say the higher and higher and closer thing. The kids will understand the closer and closer far better than this, which is why when we teach kids, we don't tell them this usually. But this is the true definition of limits that mathematicians actually use, like in sort of when we are writing proofs about things and so on. This is the correct definition to be used. Like I said, we're not going to use this very much in this class, but it is something that is super important, and it will be a main fixture of classes that you take later on if you're a math major. All right? So maybe this will entice you to become a math major if you're not already. Or maybe you've just now decided not to be a math major because of this. I hope not. It's very interesting. Any thoughts about that? This, I don't know if this sounds just like totally complicated. It is complicated, but in my opinion, actually, this is sort of one of the great towering heights of the accomplishments of maybe mathematics before the 20th century. I feel like this is very impressive to me in that it takes an idea, this sort of closer and closer, higher and higher thing is very easy for everybody to understand. And this was understood by people for many centuries. But at a certain point, the whole discipline of mathematics had matured to the point where this was no longer acceptable as a definition, because really this never was acceptable as a definition. It was just an idea that people had. But when mathematics really sort of got serious, we came up with this thing, which is some kind of like, to me, a real sort of leap in terms of the power of mathematics to understand what it is we're really talking about. All right. I can see your attention is waning at this point. So let's move on to something a little more down to earth. This is the true definition of a limit. It's very strange, and it is super important, although, to be honest, we're not going to do much with it in this class. All right? So let's talk about how we are going to find limits of a sequence. Finding limits of a sequence finding limits of a sequence. This usually is basically the same as finding limits of functions. And so in general, you don't really need to think about special tricks for limits of a sequence, because you can usually think of them as functions. So if an has a formula that looks like a continuous function, f of x. I'm talking about, like n minus 1 over n. This, as a formula, looks basically the same as x minus 1 over x as a continuous function, right? an equals n minus 1 over n. As a sequence, is really the same kind of a thing as that function over there. And we already know many tricks to find the limits of that function over there. So if an has a formula that looks like a continuous function f of x, then in this case, the limit as n goes to infinity of an will be the same as lim x goes to infinity of f of x. And so everything that you know about finding the limit of a function, you can use that to find the limit of the original sequence. All right. And usually this will get you pretty far. So for example, something like, what is lim n goes to infinity of 32 plus 3 over n? Well, that's a sequence. Like, technically this is a sequence, and it is not a continuous function when I write it this way, because this n is only allowed to be the whole numbers, 1, 2, 3, 4, up to infinity. So it's not really a continuous function. But I can consider this as being the same as the continuous function 32 plus 3 over x, right? So this is really the same as the limit of a continuous function, 32 plus 3 over x. And then can someone say, what's the limit of that? It is 32, yeah, because you know the 3 over x part becomes 0 because the denominator goes to infinity and becomes 0, and you just are left off with 32. All right. Actually, the same. I mean, you could have applied exactly the same reasoning to the beginning right here. But there are fancier tricks for the limits which you can also use. For example, what about the limit of the sequence n over e to the power n? As a sequence, this is a very weird sequence of numbers, I guess. I mean, you can try to plug in a few values. 1 over e, 2 over e squared, 3 over e to the third, and so on. And from that point of view, it's not obvious how you would find this limit, but you can turn this into a continuous function, x over e to the x, and that is a nice ordinary looking function. X over e to the x. And then what... how would you find this limit? Yeah?
L'Hopital's rule.
Yeah, you got to use the L'Hopital's rule here. If you try to just sort of make x go to infinity, you will see both the numerator and the denominator both go to infinity. So this looks like infinity over infinity, which means I'm going to use L'Hopital's rule. And I should take the derivative on the top and the bottom. I hope everybody remembers how to do that. X going to infinity. It's going to be 1 over e to the x. If I take the derivative on the top and the bottom. And then what's this limit going to be? That's 0, right? It's going to be 1 on top, and then the denominator is becoming infinite. And so this is 0. All right? So I don't know if anybody was wondering before I said all that. Am I allowed to use L'Hopital's rule for the limit of a sequence? The answer is basically yes, you are. And you can use any of the tricks that you know about limits for continuous functions. They apply to sequences also. As long as your sequence is given by a formula which also looks like a continuous function, then you can use all of your favorite tricks for limits. All right? All right, and so maybe I might as well just say this. So because of all of that, we get all of our favorite limit rules from the usual continuous functions. And I'm going to write down a big list here. These are usually things that you don't even think about because you use these rules so often. But for instance, there's a rule that says, well, I'll just write the version for sequences. Lim n goes to infinity of an plus bn. So if you have two sequences added together and you take the limit of each of them, there is a similar rule about functions. If you have two functions added together and you take the limit of each. Does anyone remember what you get here? This is a rule that I'm sure you all know how to do, and you kind of do it without thinking about it. But what if you have two things added together and you want the limit?
You can split it into two limits.
Yeah, you can just do the limit of each of the two parts. Like he said, you would split it into two limits. So this is equal to lim of an plus lim n goes to infinity of bn, right? So this is what I mean by limit rules. That's the sort of basic rule of limits. If you are adding two sequences together, the limit of the two things added together is equal to the first thing plus the limit of the first one plus the limit of the second one, right? Actually, in a sense, we already used this one when we were talking about this example right here. Here I have two things together, and nobody objected when I said, well, the 32 just stays like it is, and then 3 over x turns into 0. What I was doing in my head was considering these as two separate things and doing the limit of each one. And this is legal. Really, it's because, well, if you think of them as like functions, then this is already a rule you know about functions. All right, similarly, I'm just going to write a big list here. This is, we are usually not going to sort of, like I said, you usually do these kind of in your head. So it's not typically necessary to look at this big list and remember these formulas. But if it's subtraction, you can just subtract them. So this is lim of an minus lim of bn. If it's, there is a rule about multiplication by a constant. Anybody remember something about this? If you have a constant multiple inside of a limit?
You can pull the constant outside the limit.
Yes, you can pull the constant outside of the limit. Like so. This is all that's true about functions. It is also true about sequences. Another one. This is a lesser known one, maybe. If you have two sequences multiplied together, you can also split a limit like that. I hope everybody knows you cannot split a derivative like that because you have to use the product rule. But if it's just a plain limit, you really can just do lim of the an times the lim of the bn. All right, this also works for quotients. I'm just going to write two more. It also works for quotients. I will say mostly an over bn equals lim of an divided by lim of bn, provided that, anybody know there's actually a little technicality that you have to say here. This is only valid provided that. Anyone got an idea? Yeah?
The bottom is greater than 0.
Yes, the bottom limit cannot equal 0, right? Because if the bottom limit was 0, then the right-hand side of that equal sign wouldn't be a real number. So the whole thing would be bogus. So provided that the limit on the bottom, n going to infinity, bn, is 0, right? If that limit is 0, then actually you can't do this this rule because it wouldn't make sense anyway as soon as you wrote the answer. All right, and then finally, one last thing. You can do this also with exponents. And this is the whole list that is written in our book. Like I said, I don't expect you to memorize these per se. You kind of use these all the time without even thinking about them. So I'm not often going to refer to this list. But the limit of an to the power p. What should this look like? Here's what it isn't. Limit of an times limit of p. Something like that. It's not that. Yeah, what you can do is, don't do that. This doesn't really make much sense. This is an to the power p. You don't turn it into multiplication like that. You have the power of p, it's like this, right? This says if each individual term is being raised to the power p, and you take the limit of that, that's the same as taking the limit of the terms themselves and then raising the limit to the power of p. This one is maybe less obvious, but this one is still true. In order for this to be true, this is true if the p is greater than 0. If the p is negative, then if the p was negative, then this thing sometimes would look like a 1 over or something or other, and then you'd have to worry about things being 0 or not. And so I'm just going to say this is always going to be true if the p is greater than 0 and the an is greater than 0. Also, for other reasons, if the an itself are negative, then these exponents may not be well defined. If you have something like minus 1 to the power half is not a real number. So you also need to require that these guys on the inside are positive. All right, these are the rules for limits. And like I said, these things we are going to use all the time, really without even thinking about them. All right, but maybe just for now, we can actually write a couple examples where we do kind of write them in full detail here. For example, what if I wanted to do the lim of n over n plus 1? All right. Now this one you could rewrite with x's and then use L'Hopital's rule if you wanted to, although I'm going to, instead of that, I'm going to try to use the laws for the limits that we were just talking about here. Actually, as is, you might be tempted to just say, oh, this is a quotient, and so I can do the lim on the top and the lim on the bottom. But actually, those lims on the top and the bottoms would be infinity both times, and so this is not going to get you a good answer. Rather than doing that, I'm going to simplify a little bit first, and this is a typical trick that you do when doing limits involving sequences and fractions. I'm going to divide by n on the top and the bottom. This is similar to how you handle like rational functions. So this is going to become still lim here, n goes to infinity. Dividing by n on the top, n becomes 1 over n. So let me just, no, it doesn't. It becomes 1. I'm doing 1 over n on the top and the bottom, right? This is what I mean by divide by n on the top and the bottom. Up top, it simplifies to 1. And on the bottom, distribute that thing down there, I get 1 plus 1 over n, like so, all right? And now we can use my various laws about limits on the top and the bottom or whatever. So this is a limit of a quotient. I can turn that into limits on the top and limits on the bottoms. So this would be lim on the top of 1. And that, of course, is going to just equal 1 up top because there's no n's. And then on the bottom, lim of 1 plus 1 over n. And then on the bottom, so on the top, that's just 1. On the bottom, I can do my limit of a something, and now it looks like 1 plus lim n goes to infinity, 1 over n. And then that limit right there is 0. This is a fraction in which the denominator is becoming infinite, and the numerator is just 1. So this, my final answer would be 1 over 1 plus 0, which is 1. All right? Now, ordinarily, I would expect you to basically do all of that in your head, although I might ask you to, on the homework or something, write out specifically step by step using the various limit rules. Yeah?
Could you use L'Hopital's rule?
Yes. Yeah, this one also you could have right at the beginning, change this into a continuous function, x over x plus 1, and then do L'Hopital's rule. That would also work. Yeah. But I'm trying to demonstrate the rules here. All right? Yes?
What is the indicator that you have to use a limit rule? What's telling me oh, I gotta do top and bottom thing?
I'm not sure exactly what kind of answer you're looking for. I mean, you mean rather than using L'Hopital's rule or something like that?
Yeah.
So I would say in general, if I'm just asking you on the homework or whatever, do this limit, then you can do whatever seems best to you. So if you prefer the L'Hopital's rule, that's fine. Although I might say something like, do this limit using the limit rules, and then you should do it this way. Yeah. But like in general, there's no sort of special reason why you should do it this way versus the other way. Yeah. Great. All right, we got a little bit of time left. Let's talk about another important example here. How about, I had one more of those. Yeah, it's fine. Here is an important example. What about an equals minus 1 to the n? This is a very simple sequence which involves an alternation of signs and sort of nothing else, right? If you were to write the terms out here, it's minus 1, 1, minus 1, 1, etc., right? And this one you have to be a little careful about if I ask you to find the limit of this sequence. So to find lim n goes to infinity of this thing, minus 1 to the n. For this one, actually, you can't translate that into a continuous function and then analyze it in that way. So to find this limit, you can't turn it into a continuous function like this, f of x equals negative 1 to the x. That's because an exponential function is only well defined if the base is positive, right? Just because, for example, you could, if this were a real continuous function, you could do something like minus 1 to the power half, minus 1 to the power half, which would be the square root of minus 1, which is not a real number. So like this as a function is not a nice continuous function of real numbers. So that is not the appropriate approach. You really have to think about this thing as it is, right? And this is true of many sequences. They just can't be translated into continuous functions, and so you have to treat it just as a sequence. Anybody have a feel for this? Does this converge to anything in the limit? Does it approach any particular value? I think the answer is no. This thing has no limit. This is not approaching anything. So in this case, you can't think of it as a function. I guess that's what I just wrote and then X'd it out. Can't think of it as a continuous function. You have to just think about the values. And in this particular example, the values are obviously not approaching any particular limit, right? Some of them are positive 1, some of them are negative 1, but they are not altogether approaching a particular value. You have to just look at the values. Sometimes it's helpful to try to sort of graph the sequence and what that looks like. I'm not going to draw like a smooth line, but you can still draw sort of the graph of a sequence by using, 1, 2, 3, 4, like this. And then the sequence values go minus 1, and then 1, and then minus 1, and then 1, and then minus 1, etc., right? Sometimes you'll see people drawing the graph of the sequence. It's not going to look like a nice continuous line because this is not the graph of a function, but it is. Those are the sequence values, and you can see by looking at the graph here, these values are not approaching any limit. So there is no limit here. All right. It don't approach anything. There is a nice trick that we can use sometimes. So I just have one more example in our remaining 3 minutes. How about minus 1 to the n over n? All right. If I were to write the terms of this one, they would look like, so when I use n equals 1, I get minus 1 over 1. That's 1. If I use n equals 2, it's minus 1 squared, so that's a plus over 2. So this is minus 1 first, then 1 over 2. Next, I use n equals 3. It says minus 1 to the 3, which is a minus sign, and then 1/3. So this is minus 1/3. What you get is these same fractions but with alternating signs. 1/6, etc., right? Is there a limit of those things? These ones, the signs are alternating, but the fractions themselves are all kind of getting close to 0, I would say. Is that what you were going to say? Yeah, these are approaching 0, although the graph, if you think of these points on a graph, what they do is, the first one is down here, the next one is up top. They do this kind of a thing, right? They are going back and forth, positive, negative, but they are getting closer to 0 as they go, all right? And so this one actually does have a limit, and it equals 0. Now you can tell this by looking at a graph, but here's a cute trick for showing. This kind of comes up often. A cute trick for showing that the limit of something equals 0, which this one does, right? -1 to the n over n is what we're talking about. I would like to demonstrate that it approaches 0. The problem is, just like the one we talked about a moment ago, you can't think of this as a continuous function because of the -1 to the power n. You can't just change that into -1 to the power x. But here's the trick. A trick for showing that the limit of sequence goes to 0. Instead, show that the limit of the absolute values equals 0. All right? Certainly, if the limit of the absolute values goes to 0, then that means the original sequence also goes to 0, right? If you just ignore the signs and show that the whole thing goes to 0, if the absolute values go to 0, the original thing must also go to 0. This is the trick. And so, but the reason this is a good trick is this right here, actually you can turn into a function. So what I mean is I can do, instead of -1 to the n over n, we consider absolute value -1 to the n over n. And can we simplify this absolute value there? It actually helps to have the absolute value there. What's the effect of that? I know it's time to go. Someone want to shout it out? The absolute value, of course, makes everything positive, right? Things which used to be negative stays the same number, but it becomes positive. Yeah. Yeah, it just like kills the weird negative thing on the top, right? He said it just turns into 1 to the n over n. This really is just like 1 over n, right? The only effect of this thing on top is sometimes it's +1 and sometimes it's -1. But when you're taking the absolute value, it's always going to be +1, right? And then this part right here, when I do, so the limit as n goes to infinity is 0, because 1 over n has limit 0. All right, we'll do some more, well, I guess next week. Next time will be the test. Please let me know if you want to get together and go over test questions or anything. I would be happy to.